Hey everyone, welcome. Today, we're digging into a recent issue of Biostat Weekly. And what starts as a pretty simple question about whether we have too many scientists, well, it kind of unfolds into this amazing story about the future of research itself. It's about the people, the incredibly complicated problems they're up against, and the powerful new tools they're building to solve them. So, let's jump right in.
So it all kicks off with this one number, 400,000 plus. That's how many postdoctoral researchers have been recruited in China over just the last 4 decades. I mean, that's a wild figure, right? And it really sets the stage for pretty interesting debate.
And that question is, and this is pulled straight from the headline and the source material, are there too many postdocs? Now, it sounds simple, but as we're about to see, digging into that question actually tells us about a massive shift in how science even gets done.
Okay, so to really get this, we've got to step back and look at the bigger picture behind this rising tide of researchers. I mean, where is this huge wave of talent even coming from? And what is it for?
I mean, just look at these numbers. The scale of this program is, wow, 40 years, over 8,800 research stations. But the real kicker is the speed. They recruited a record 42,000 researchers just in 2024. This isn't just a workforce. It's like a scientific army being assembled at an incredible pace. Which really makes you wonder, right? What's the mission?
And that's where we get to the why of it all. Turns out, this new generation of scientists, they're being drafted to solve some of the toughest, most complicated challenges in modern medicine, because the problems themselves have gotten way harder.
So, challenge number 1, the sheer complexity of chronic diseases. You know, we're living longer, which is great, but it often means we're juggling multiple illnesses at the same time. And our old ways of looking at them, one by one, just aren't cutting it anymore.
Right, so here's the deal. The old models, they're just too simple. They zoom in on a single disease, but they're totally blind to the way different illnesses connect, interact, and change over a person's life. For managing real-world long-term health today, that approach is just, well, it's not enough.
But wait, it's not just the diseases that have gotten more complex. The actual doing of science has become this incredibly tangled process with all kinds of new hurdles to jump over. So let's break a few of these hurdles down. First, you've got AI and stats. Super powerful, but how do you actually know you can trust what an AI tells you? Then there are tricky issues in clinical trials. Sometimes you have to let a patient switch to a better treatment, which is the right thing to do, but that one move can totally throw off your results if you're not careful. And then you have these massive studies, like on cervical cancer, where you have to pull together totally different kinds of data and make it all make sense together. Each one is a huge challenge.
Now, with all these huge challenges, you might think things would grind to a halt. But here's the twist. A whole new wave of AI-powered tools is showing up, giving this new generation of researchers a toolkit their mentors could only have dreamed about.
And I want to be super clear about this. AI isn't just some nice-to-have gadget. It is a total game changer for biostatistics. It's letting scientists attack these complex problems in ways that were literally impossible before.
Okay, so what are we talking about here? What do these tools actually do? Well, first up is something called Delphi 2M. Remember how we talked about those old models that only look at one disease at a time? Well, this thing just blows that wide open. It's a large language model built to predict multiple diseases at the same time, because it understands how they're all connected. This is the kind of engine that could make personalized medicine a reality.
All right, next up, we've got MLM cell type. This one tackles a whole different kind of puzzle. In genetic research, figuring out what type of cell you're looking at can be incredibly tedious. This tool automates that. And this is the really cool part. It actually gets a bunch of AIs to vote on the right answer, which makes it way more accurate. It even tells the researcher how confident it is, which is so important for good science.
And last but not least, we have something that points to a much bigger trend. Custom GitHub Copilot. Now, this isn't a medical tool on its own, but check this out. It shows how AI is getting baked right into the daily work of a researcher. They can now customize their AI coding assistant to become a specialist partner for their specific project. It's about making AI a seamless part of the workflow.
Okay, but all this flashy, cutting-edge tech, it's pretty much useless if you don't have a solid foundation to build on. I mean, you can have the smartest AI on the planet, but it's nothing without good data, reliable tools, and clear standards.
Just think about something as basic as writing a research paper. Researchers have to make a choice. Do they use a local tool like TextLive? It's faster, it's offline, and it's more secure for super sensitive data. Or do they go with an online tool like Overleaf, which is amazing for collaborating with a team? See, even these fundamental choices make a huge difference in how the work gets done.
Another piece of that foundation, and this one is huge, is sharing data. The source talks about this new national standard in China called a data paper. Basically, think of it like this. It's a paper that doesn't present new findings. Its only job is to perfectly describe a dataset so other people can find it, understand it, and use it. This is a massive step for open science.
And with all this talk about AI and new standards, it's easy to forget the basics. At the end of the day, the core skill of writing clearly and convincingly is still absolutely essential. The tech is there to help, for sure, but it doesn't replace the actual scientist.
All right, so let's pull all these different threads together. The people, the super complex problems they're facing, and this incredible new toolkit they have to work with.
So here's the journey we've been on, right? First, we saw the people, this incredible wave of over 400,000 new researchers. Then we looked at the problems they're up against, this whole new level of complexity, both in diseases and in the science itself. And finally, we explored their toolkit, a powerful mix of brand new AI and the solid, fundamental practices that make it all work.
And all of this brings us right back to where we started, but with a totally new perspective. The question isn't really whether 400,000 postdocs are too many. Given the size of the problems we need to solve and the power of the new tools they have, the real question, the one we should be asking, is this. How do we best empower all of them to succeed? And that's a thought worth hanging on to.